Okay, so welcome back, everybody, to Math 365 Partial Differential Equations. And before we get started with our new topic for the day, I want to return a little bit to the use of the method of characteristics in our solution to the wave equation, because I think there was maybe a few questions, at least on a part of that. And I want to try to explain it a little more. So yeah, in particular, we were looking at an equation that looked like this. I mean, we had two equations. One of them was for W, and one of them is the one that you're looking at. And we wanted to solve this with the method of characteristics. And there was our characteristic for this equation. And if you kind of draw a graph of what you're seeing, so here's a graph of the xt plane, and you might call this h for the upper half plane, and here's your infinite string, and you fix some point x naught, and then you look at this characteristic line, which kind of looks like that. And you could pick other initial points too and look at other characteristic lines. Doesn't really matter. And you can take this equation and solve it for x naught or x1 or x2 or x3, whatever. We note that x naught is x minus ct. And of course, same is true for x1 or x2 or x3. So on and so forth. And to be perfectly clear, so this is a graph of the domain of function u, right? So this vertical line is u 0x. This is a characteristic line in the domain, and u eventually is to be a function defined on this entire half plane. And we start out by solving it only on one of these characteristic lines. And so we got an equation like the following. So derivative of u with x of t plugged in. And in general, it's w, but we had figured out is that what we figured out for our solution for w? Well, I guess it was x plus ct. I recall this was our solution, w naught to the previous equation. So kind of picking up sort of where we were. And so when we plug in x equals ct plus x naught, we of course get x naught plus 2. CT. So we ended up with that equation. And this is now an ODE on the following line that I put in pink. Right? And so method of characteristics says you're solving this ODE on that line. So this is really a function that takes t as an input and then goes up to the line and then plugs that into u. And then you're differentiating that and it's equal to w evaluated at x naught plus 2ct. And we integrated this and we found a solution, namely just by fundamental theorem of calculus. And remember, fundamental theorem of calculus says you integrate and then add the constant. Well, what constant do you add? This is your initial condition for the characteristic line. It's u at 0, x naught. And our initial condition was u 0x equals g. So we arrived there. And then the next step, the step that I think is confusing to people perhaps, was we made the substitution that x naught equals x plus ct. And so why is that substitution valid? Why are we allowed to introduce now t back into this integrand? Did we mess up the fundamental theorem of calculus when we integrated? So those are the questions I think may have been in your mind, or many of your minds. So you have to first kind of agree that this is a solution to the equation on the characteristic line. So you have to get to that point first, but once you're there, you need to say to yourself, okay, well, how can I go from this one line in pink to any other solution? So if you have a point and you want to, like on some other characteristic line x1, you can find a solution at x1 similarly, of course. And I guess this should have been omega naught the whole time. It was our initial condition, or our initial condition for the other equation. Or if you want to solve the ODE on any other characteristic line, then you just plug in a different constant. But the point that I want to make to you is that regardless of which constant you plug in, the right-hand side of the equation stays the same. So just as a mathematical device, so as not to write down infinitely many equations, you can have sort of like one equation to rule them all, you know, and just write it in terms of the right-hand side. And then as you vary x and t, you can freely pass from one line to the other as you move about the domain. And you'll naturally be on the correct solution to the ODE. Yeah?
But then the solution that we get at the end applies to all, it's all the solution, not just on one characteristic line?
Yeah, and the way you can conceptualize that is that the solution that you get at the end, well, first of all, it absolutely does apply to the characteristic line. But the characteristic line it applies to is completely arbitrary. So your choice of x and t that you plug into the solution implicitly picks one of the characteristic lines. And because the right-hand side of the equation is the same for every constant, therefore, the formula for any of the characteristic lines remains the same. It's just a mathematical device showing you that there's just more variables in this equation than you need. The offhand comment I made last time was the reason why this is psychologically difficult is because we don't like thinking of like x naught as like varying it around. This is what I meant, but it occurred to me that I should take some time and explain it in more detail.
So it's being varied in the sense that it's arbitrary. Is that a correct way to think about it?
Yeah, it's arbitrarily chosen, and the right-hand side of the formula is the same no matter which choice that you make. So like in some sense, if you choose x naught and then rewrite x naught like the way that we do. So let's plug in x naught with this. You'll get x t. X naught becomes so when you just plug in, I'm almost off the board, but I'm only missing one parent. So that's okay. When you just plug in x minus ct in terms of x naught, me as a student, I'm thinking, well, wait a minute, this still depends on t. You can't just drop the variable for no reason and then say all of a sudden this is an independent variable, doesn't depend on t. Yeah. So I grant you that's confusing, but it's also true that even though this is now a solution for the red line, it's also the very same solution you would have got if you had been looking at some other characteristic line. And that's what I mean when I say your choice of x and t implicitly chooses one of these.
If you were to graph the solution in three dimensions with x, t, and u, would you see the characteristic lines appear in some way on that graph, or are they just like more abstract than that?
Yeah, you do see the characteristic lines appear, and when we discuss this Huygens principle, we'll talk about that further. But like another way to conceive of this. So I'm going to erase something. So is everything okay? Another way to conceive of this problem. So let's look back now at the full linear wave equation. And the first step we did was to like factor it. Well, we write LU equals 0, and then we factor operator L. But if you wanted to, say, make a coordinate change, say C equals X minus CT, and tau equals X plus CT. I mean, I'll leave this as an exercise. But here, operator L was so operator L is written in terms of x and t coordinates. So operator L is sort of on this domain with those coordinates. But if you instead want to switch coordinates to, you know, these lines and those lines, then you will find that this operator becomes, so continuing to do this trick of writing capital U in the coordinates C tau, lowercase u in the coordinates tx, then this equation now becomes something like that. So whereas what I did, I just factored the operator, and each of the individual factors becomes a partial derivative, like in either one of those. And why do I say that? Because you're asking about, like, do the characteristic lines kind of appear geometrically? And yeah, they appear geometrically in the sense that there's a natural coordinate system, the characteristic coordinates, about which solving this equation is nothing but differentiating in the two coordinate directions. And now this equation becomes super easy to solve. So then you might say, why didn't you do this in the first place? But you still have to deal with the boundary conditions. And when you do that, I don't think it makes it any easier. Plus, I want to show the relationship to first order equation and you know, this reduction technique. Okay. Any further questions on that process? Yeah, so just based on how last class went, I thought maybe I could preempt a few office hour discussions and just try to do a little bit better job explaining what's going on there in theory. Yeah, and so I want to return now to actually a few fundamental concepts, a few technical concepts. So one way that you could approach this class is to start out with a bunch of technical definitions and so on and so forth, and then having established that, start to solve PDE. I kind of like to do it a little bit differently. I like to solve something first and then go back and maybe refine the language that we're using. And so that's what I'll do now. So partial differential equations, they are operators on domains. But we need to be clear, like, what is a domain? What is the boundary of a domain? What is an open set? And maybe a couple more things. So that's what I want to take care of. So generally speaking, I want to consider a PDE operator on a domain, which we'll call D. And so a domain is a connected open set. And so I need to tell you what is a connected set, what is an open set, so that you can know what are the things that are allowed for PDEs to operate on. And these domains, they're always going to be subsets of Rn. In many of our examples, it'll be R2, R3. You've already seen the upper half plane is an example of a domain. It's a connected open set. Certainly the interior of a disk or a ball is sort of like the most basic domain you can have, but there's many, many other wild examples. Intuitively connected, like if you take an open disk and another open disk and they don't intersect, that's not a valid domain. That's two separate domains, right? So that's your intuition, but actual definition is maybe a little bit more intricate. So the reference material for this is section 2.3 of Borthwick, and I'll make some comments maybe on the way he does things, and also go over it. These definitions properly live in the field of topology. If you take that course, you'll learn like more general definitions. And indeed, PDEs can exist on more general regions than subsets of Rn. But but that's not what we're doing here. So these definitions are kind of maybe specialized to the situation of Rn. So you should understand that there are more general versions. And I don't want to sort of digress and get into that ad nauseum. Sort of want to cleanly say what we're talking about and then move on to solving more PDEs. So you are open. D is open if it is a union of open balls. An open ball is what you think it is. Center X, radius R. So open ball is the collection of points inside Rn. Open ball with center X is the collection of points Y in Rn, such that the distance from Y to the center is less than the radius R. And so here I'm using distance in Rn. So this is just if you write out X in coordinates, length of X is square root of sum of the squares. I mean, all that is saying is that if you pick some point X and you pick some radius R, then you're just looking at the set of all points Y such that their length is less than that radius. Strictly less than. And that's called an open ball. And take an arbitrary union of them, finite or infinite, doesn't matter. And that's what's called an open set. And there's a test for an open set. So set U is open. So here's some outline of set U, but maybe not including the boundary. So set U is open if for any X inside U. You can always find some radius such that the ball of radius R around X is contained inside U. Got like a question? I see. And so U is open if for any X in U. Have you seen this symbol? There exists, if for any X in U, there exists some radius with the ball of radius R about X, completely contained inside U. This is completely equivalent to the other definition because you just take the union of all the balls of this form, that'll be equal to U. On the other hand, I won't show it, but on the other hand, if you take a set who's equal to the union of open balls, then yeah, this will always be possible to do. Any question on that? So open sets like in R2 and R3, they're exactly what you're used to. They are these sets that do not include their boundaries in some sense. What does it mean to be connected? Well, actually what I'll do it this way. So set is path connected if, so here's your set D. A set is path connected if for any two sets, any 2 points inside that set, there exists a path between them. A path, of course, is a function f from a continuous function f from 0, 1 into D with f of 0 equals x, f of 1 equals 1. I mean, just a path would be any continuous function from the interval into Rn, but your path connected if for any 2 points inside the set, there's a path that stays inside that set that connects those 2 points. If you take a topology class, you will learn a more general definition of connected, but it doesn't matter because in Rn, path connected and connected are the same thing. In fact, your textbook author defines this to be connected, but he's using an equivalence. But just be aware that properly this is called path connectedness, and there's a more general definition if you take that topology class. So I've defined open set, I've defined connected set, so a domain is an open connected set. By the way, so a set is closed. Closed if the complement is open. So for example, the closed ball in Rn so it's going to be all the points y such that distance from x to y is less than or equal to r. That's closed because take the complement of this, it's everything outside. And so for any point outside, you can always sneak in a ball of radius r that stays outside in the complement. In R1, the complement of a closed interval is open, and therefore a closed interval is closed. That's where these terminologies come from. An open interval in R1 is, of course, open. Every open interval is a ball of a certain radius, but in R1. And every open set in R is a union of intervals, certainly. I'm flying through this really fast. I'm not intending to give you like a super deep understanding, but I do want to say words and have them mean something. So what's the boundary? Consider an open set like this ball of radius r. So this is an open set. Even though it's open, it has a boundary that I'll trace out. And how can I define this? So I can say that, so let's take our setup. D is a domain. Okay, so D is a connected open set. For instance, D is the open ball of radius r. So how do we define the boundary of D? So a boundary of D is the collection of the following points. So let's say that W in Rn doesn't need to be in D. W in Rn is a boundary point if what? Well, there's three kind of things, right? You can be on the interior, meaning that there's a ball around you that stays completely inside D. Or you can be on the exterior and like there's going to be a ball around you that's completely outside of D. I want to identify this intermediate case where you're a boundary point if for any open ball around you, there is some point inside D and some point outside of D. So I just need to say that in mathematically precise words. So if for any open ball of radius S about W, well, let's say it like this. If any open ball of radius S about W contains a point in D and in D complement, you have to have both. And if you do that, then you're a boundary point. And then we'll define the boundary of D to be the set of boundary points. So in this case, domain D was a connected open set, and its boundary was the circular region where your distance is actually equal to R, not just less than R. In an analysis class, you will use this definition to prove that for any boundary point, there's going to be an infinite sequence of points inside D that converge to the boundary point. So they're also called limit points. Then you can say the closure of D, which you write D bar, is D union its boundary. So the closure of the open ball is the closed ball. Okay, and so the way you set up a PDE is you start with some operator, L, for instance, wave equation. But it's not just L on the abstract. It's defined on a domain of points, or it operates on functions whose domain is D. So operator on more properly on C2 functions on D, but operator L on domain D, and D being connected and open. And so you will write like LU equals F on the connected open set. And you'll write something like U restricted to the boundary of D equals some function. And in the case of the wave equation, you also write the derivative of U restricted to the boundary equals some other function. And so this is how you kind of properly set up an equation with its initial condition. The equation actually operates on the open interior. And then you have these boundary values. So a solution U is defined actually on the closure of D. And it satisfies these properties. That when you restrict to the boundary, you get these functions. And on the interior, you can differentiate. If you try to differentiate at the boundary points, you'll have problems because differentiation typically requires an open set to make it work out. There's other problems too. But so just to be clear, that's the setup we're talking about. And so for the wave equation, D was something like for a D'Alembert's wave equation, domain D was R and then cross product with this half open interval. So the upper half plane. Closure of D would just be including that endpoint, including that boundary. So on and so forth. So one more thing. So given a function, f on some, well, let's just say Rn, or on a domain or on a closure of the domain, it doesn't matter. I want to define the support of f, which you write as SUPP. The support of f is the closure of the set of points closure of the set of points x with f of x not equal to 0. So intuitively, the closure is kind of like the set of places where f of x is not 0, but it's not exactly that. It's that including all the boundary points. The reason why I mentioned that is so that I can at least talk about the one-dimensional version of Huygens' principle. So you go back to a D'Alembert solution of wave equation. Saying something like this, like, so this was in the context of the problem we solved last time, the initial conditions, g and initial velocity h. And we go back and look at this setup. And you suppose that now that g is supported on some interval, a to b. So you draw some interval. So remember, this is the initial time equals 0. Position, and so like the graph of g, who knows what it looks like, but it's 0, 0, 0, non-zero out here, and then as you go past down a, it's 0 again. Maybe in xtu coordinates, like if this was it's kind of hard to draw, but you could imagine that as time goes, you could see this wave kind of like traveling down, but you're sort of 0 outside of that position. And so Huygens' principle is basically telling you the following. So it's telling you that if you take this solution and just kind of stare at it, then the information that you start with, that is to say your initial condition, it cannot travel faster than the propagation speed. So like, if you look at your text, there's kind of a movie where you can see all the different time slices, and you can kind of see this splitting into 2 ways and traveling off. And this information, this non-zero part, can't move faster than c. So if you look at the set of values in the domain where this formula can be non-zero, looks like this. So you kind of draw this line. This line is like b plus ct. And you draw this line, a minus ct. So if you look at this entire space, this is the range of values in the domain. I'll sort of draw it out here. What is it? Where your wave can exist, and you have to be 0 outside of that, at the side of that box. So, by the way, there's your characteristic lines showing up in the solution, which is quite cool. And there's a little bit more to say about it. So, but I won't, other than just drawing this picture, at least not till Monday. So this is eminently puzzle throughable. So what is it on this region? This function has to vanish. Basically, if you start here, you can travel up this way, or you can travel down that way, but you can't be non-zero here. And because this vanishes, it'll actually be true that this term reduces to the integral from A to B. And so your wave equation is actually a constant on that region. You just play with some algebra inequalities and you can see it quite quickly, but maybe I'll show you on Monday, but I certainly challenge you to do that. And that's called just Huygen's principle, that really this signal can't go faster than the propagation. And of course, in special relativity, of course, you can't send information faster than the speed of light. And that becomes now the basis of a whole theory of relativity. The relativity equations are a little more complicated than the linear wave equation, but the Huygens principle holds. Okay, so thank you everybody for your time and attention, and we'll see you on Monday. Take care.